Tonight, we're going to explore something that can permanently change the way you see your place in the cosmos. We're going to discover just how small Earth really is. And I'm not talking about comparing it to the Sun or to Jupiter. I mean the true scale, the scale that makes Earth almost disappear. Because here's what most people don't realize. Earth isn't just small. It's so unbelievably tiny that, at a certain point, language starts to break down. You try to describe it, and the words feel inadequate. And by the end of this journey, I think you'll see our planet and yourself in a completely different light. Before we dive in, if you enjoy these kinds of deep explorations of space and perspective, a quick like and a subscribe genuinely helps this video reach more people. It's small on your end, but it makes a real difference. Now, let's begin. Let's start with Earth itself. Our home, the world we walk on every day. From down here on the surface, Earth feels enormous. You could spend your entire life traveling and still never see every corner of it. Continents stretch for thousands of miles. Oceans cover about 71% of the surface. Mount Everest rises nearly 30,000 feet into the sky. And for early humans, Earth was everything. It was the universe. The sky above felt like a dome with lights on it. The ground beneath seemed flat, stretching forever in all directions. And based on what they could see, that made sense. When you look out at the horizon, Earth looks flat. The curve is simply too subtle to notice unless you get high enough. Earth has a diameter of about 7,926 miles at the equator. If you wanted to walk around the equator and somehow you could walk on water, you'd cover about 25,000 miles. At a steady pace of 3 miles per hour, walking 8 hours a day, that would take you about 3 years and a month. That's a long walk. From a human perspective, Earth is genuinely large. The surface area of Earth is about 197 million square miles. And to frame that in a way your brain can actually hold on to, imagine this. If you wanted to visit every square mile, and you spent just 1 second in each location, it would take you over 6 years of non-stop travel. Even the United States, one of the largest countries, covers only about 3.8 million square miles, less than 2% of Earth's total surface. So yes, at human scale, Earth feels vast. But here's where things begin to shift. The moment you zoom out just a little, the moment you start comparing Earth to other objects in space, Earth begins to shrink. Not physically, of course, but in significance, in proportion. Earth stops being everything and becomes one thing among many. And as we keep zooming out, it gets smaller and smaller until it becomes something almost impossible to see at all. So our first stop is our nearest neighbor, the Moon. The Moon orbits Earth at an average distance of about 238,855 miles. That's roughly the distance you'd travel if you drove around Earth's equator 9.5 times. It feels far, and by human standards, it is far. When the Apollo astronauts traveled to the Moon, it took them about 3 days to get there. The Moon itself has a diameter of about 2,159 miles. That's roughly 27% of Earth's diameter. So yes, the Moon is smaller than Earth, but not dramatically so. If Earth were a basketball, the Moon would be about the size of a tennis ball. But here's the part most people never visualize correctly. The distance between Earth and the Moon is about 30 times Earth's diameter. Imagine placing 30 Earths in a straight line between us and the Moon. That's how much empty space sits in that gap. And when you see pictures of Earth and the Moon together, they're usually shown much closer than they really are. In reality, there is a vast amount of nothing between us and our closest companion. This is your first real hint that space is mostly empty. Even in our immediate neighborhood, distances are enormous compared to the sizes of the objects themselves. And the Moon's relationship with Earth is actually unusual in our solar system. Most moons are tiny compared to the planets they orbit, but our Moon is relatively large. In fact, the Earth-Moon system is sometimes described as a double planet because the Moon is so substantial compared to Earth. And that size has consequences. The moon creates the tides we experience every day. It also helps stabilize Earth's axial tilt. Without the moon, Earth's axis might wobble dramatically over time, causing extreme climate variations that could make complex life difficult or even impossible. Now, when you look at the moon from Earth, it appears about the same size in the sky as the Sunday. That's a coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. And that coincidence gives us total solar eclipses moments when the moon perfectly covers the Sunday. The moon is also slowly drifting away from Earth. Each year, it moves about 1.5 inches farther away because of tidal interactions. Billions of years ago, the moon was much closer, and a day on Earth was much shorter, perhaps only 5 hours long. But for now, the moon remains our closest companion in space. And in 1969, humans walked on its surface for the first time, a moment that showed what we're capable of when we push the boundaries of exploration. Now, let's examine the Sunday. Because the sun is where Earth's dimensions truly begin to fade. The sun is the reason we exist. Without its light and heat, Earth would be a frozen rock hurtling through space. But it is also the object that makes Earth feel, suddenly, very small. The sun has a diameter of about 864,000 miles. That's about 109 times Earth's diameter. And the sun's volume is so immense that approximately 1.3 million Earth-sized worlds could fit inside it. Pause on that. Every mountain, every ocean, every city, every person who has ever lived, all of human history. It all happened on a planet whose volume is less than 1/1,000,000th of the sun's interior. And the sun dominates our solar system in a way most people don't fully appreciate. The sun contains 99.86% of all the mass in our solar system. Everything else, combined planets, moons, asteroids, comets, is only 0.14%. Earth is not the main object in this system. Earth is a passenger. Now let's talk distance. The sun is about 93 million miles away from Earth. We call that distance 1 astronomical unit, 1 AU. Light from the sun takes about 8 minutes and 20 seconds to reach us, which means if the sun suddenly disappeared, we wouldn't know for over 8 minutes because the light telling us it was gone would still be traveling toward Earth. And to make that distance feel real, imagine a vehicle holding highway speeds. It would take about 176 years to cross that 93 million mile gulf. Even the fastest spacecraft, humans have built the Parker Solar Probe, takes months to reach the sun, even though it travels at speeds exceeding 400,000 miles per hour at its closest approach. And here's another humbling detail. The sun is actually a fairly ordinary star. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It's about 4.6 billion years old, roughly middle-aged. It has enough fuel to keep shining for another 5 billion years or so before it begins to die. The sun's power is staggering. Every second, it converts about 600 million tons of hydrogen into helium through nuclear fusion. That releases an enormous amount of energy. In fact, the sun produces more energy in 1 second than all of human civilization has produced in its entire history. The surface temperature of the sun is about 10,000 degrees Fahrenheit. The core, where fusion happens, reaches about 27 million degrees Fahrenheit. And the pressure at the core is about 260 billion times Earth's atmospheric pressure. The sun also produces solar flares and coronal mass ejections, massive releases of energy and matter from its atmosphere. When they're directed toward Earth, they can cause beautiful auroras near the poles. But they can also disrupt satellites, power grids, and communications. And there's something else the sun reminds us of. Earth is not the center. For most of human history, people believed Earth was the center of everything. It took thinkers like Nicolaus Copernicus and Galileo Galilei to show that the sun was at the center of the solar system, and Earth orbited it. And that was humanity's first major lesson in cosmic humility. Now, our solar system extends far beyond Earth and the Sunday. So let's zoom out again and see where Earth fits inside this larger structure. The inner solar system is home to the rocky worlds. Mercury hugs closest to the Sun, baked and frozen in its extreme orbit. Venus follows, shrouded in a toxic atmosphere. Then Earth, our blue marble at the right distance for liquid water. And Mars rounds out the inner worlds, a cold desert that once knew flowing rivers. These 4 terrestrial planets cluster relatively close to our star, all within about 1.5 times Earth's distance from the Sunday. Between Mars and Jupiter lies a wide region populated by the asteroid belt. Thousands upon thousands of rocky fragments, building blocks that never quite became a planet. The largest object there, Ceres, spans only about 580 miles. More than 13 Cereses could line up side by side across Earth's diameter. And despite the fact that the asteroid belt contains millions of objects, it is mostly empty space. If you flew through it, you likely wouldn't see an asteroid with the naked eye. The distances between them dwarf their tiny sizes. Then you reach the realm of giants. Jupiter dominates the outer solar system, like a king surveying its domain. With a diameter of about 86,881 miles, Jupiter is about 11 times wider than Earth. Its volume is so enormous that 1,321 Earths would barely fill it. Jupiter contains more mass than all the other planets combined. And if Jupiter were a hollow sphere, you could fit every other planet inside it, with room to spare. And yet, even Jupiter is tiny compared to the Sunday. About 1,000 Jupiters could fit inside the Sun's volume. Saturn comes next, nearly as impressive in scale. With a diameter of about 72,367 miles, Saturn could swallow 764 Earth-sized worlds. But Saturn's most famous feature isn't just its size. It's the rings. Countless particles of ice and rock extending tens of thousands of miles from the planet. And yet, remarkably thin. Scaled down, if Saturn were the size of a basketball, its rings would be thinner than a piece of paper. Beyond Saturn, the ice giants Uranus and Neptune orbit in the cold darkness. Both are smaller than Jupiter and Saturn, but they still dwarf Earth. The volume of Uranus equals roughly 63 Earth-sized planets. Neptune could accommodate 57 Earth-mass bodies in its interior. And these distant worlds take decades or even centuries to complete a single orbit around the Sunday. Neptune, the most distant planet, requires 165 Earth years to make one trip around our star. Beyond the planets lies the Kuiper Belt, stretching outward for billions of miles, a region filled with icy bodies left over from the solar system's formation. Pluto, once considered our 9th planet, lives here among thousands of similar frozen worlds. Pluto is only about 1,473 miles across. About 5.4 Plutos could line up across Earth's diameter. The Kuiper Belt is a vast reservoir of primordial ice, a frozen archive of materials from the solar system's birth. But even the Kuiper Belt isn't the true edge of the solar system. Far beyond that, almost incomprehensibly distant, lies the Oort cloud, a vast spherical shell of icy objects surrounding our solar system like a bubble. It begins at about 2,000 times Earth's distance from the Sun and extends outward to nearly 2 light-years, almost halfway to the nearest star. Objects out there are so distant that they're barely held by the Sun's gravity. No human eye has ever seen an Oort cloud object directly. We know it exists because comets occasionally fall inward from that distant realm, their icy surfaces vaporizing as they approach the Sun's warmth. And the point is simple. Our solar system is vast, trillions of miles, and in all of that space, Earth is one small, rocky world, orbiting at a distance that's relatively close to the Sunday. In a proportional model where the Sun is the size of a basketball, Earth would be no larger than a peppercorn placed 26 feet away. And you'd need a football field just to show Neptune's orbit at that scale. Now, Let me slow down here, because the next part is where the scale becomes harder to feel, even if you understand it intellectually. Because once we leave the solar system, the distances stop behaving like anything in daily life. They stop being far. They become something else entirely. This vast region marks the true edge of the solar system. Beyond the Oort cloud, the sun's influence becomes negligible. Space becomes interstellar, the realm between stars. And in all this enormous volume, Earth is one small rocky planet, about 8,000 miles across, orbiting one astronomical unit from the Sunday. The solar system extends for trillions of miles, and Earth occupies only a tiny fraction of that space. Now, let's leave the solar system and venture out to the nearest stars. This is where distances become so large that our usual measurements stop making sense. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It's about 4.24 light-years away. A light-year is the distance light travels in 1 year, which is about 5.88 trillion miles. So Proxima Centauri is about 25 trillion miles away. Here's a way to visualize that scale. Remember how the Sun is about 93 million miles from Earth. Proxima Centauri is about 268,000 times farther away than that. If the distance from Earth to the Sun were 1 inch, the distance to Proxima Centauri would be about 4 miles. And this is where the human mind starts to lose its grip. Not because the math is hard, but because your intuition has nothing to attach to. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object. It's been traveling for over 47 years. Right now, it's about 15 billion miles from Earth, moving at about 38,000 miles per hour. At that speed, Voyager 1 would still need about 73,000 years to reach Proxima Centauri. And it isn't even headed in that direction. Even if we imagine hypothetical future technology, if we could build a spacecraft that traveled at 10% of the speed of light, which is far beyond anything we can currently do, it would still take over 42 years to reach Proxima Centauri. The distances between stars are genuinely, almost incomprehensibly vast. And here's what makes that feel even heavier. Proxima Centauri is our closest neighbor. Most stars are much farther away. Sirius, the brightest star in our night sky, is about 8.6 light-years away. Betelgeuse, the red supergiant in the constellation Orion, is roughly 700 light-years away. And those are still considered relatively nearby by cosmic standards. At these scales, Earth doesn't just shrink, it vanishes. If you were standing near Proxima Centauri and looking back toward our solar system, you wouldn't be able to see Earth at all. Even with a powerful telescope, the Sun would be visible as a bright star. But Earth would be lost in its glare. A tiny dot too close to its star, too faint, too small to pick out. So let's linger for a moment at this nearest star, because it helps the scale become real. Proxima Centauri is a red dwarf, the most common type of star in the galaxy. It's much smaller and cooler than the Sunday. Its diameter is only about 129,000 miles, roughly 14% of the Sun's diameter. It has only about 12% of the Sun's mass. And because it's so small and cool, it burns its fuel very slowly. It will keep shining for trillions of years, long after the Sun has died. In fact, no red dwarf anywhere in the universe has ever died of old age. The universe simply isn't old enough yet. Every red dwarf that has ever formed is still shining today. That single fact tells you something profound about time in the cosmos. We think in decades, in lifetimes, in centuries, if we're being ambitious. But the universe thinks in spans so long that entire classes of stars haven't even had time to complete their full life cycles. Proxima Centauri is also a flare star. It regularly produces powerful flares, sudden releases of energy that can temporarily increase its brightness. Those flares would be bad news for any planet hoping to host life. The radiation from a major flare could strip away a planet's atmosphere or sterilize its surface. And yet, Proxima Centauri does have at least 2 known planets. One of them, Proxima Centauri b, orbits in the star's habitable zone, the region where liquid water could exist on a planet's surface. But given the flares and radiation, life there seems unlikely. Still, it's fascinating that the nearest star to us has planets at all. It's a reminder that planets are not rare exceptions. They appear to be part of how star systems work. Proxima Centauri is part of a triple star system with Alpha Centauri A and Alpha Centauri B. All 3 stars are gravitationally bound, forming a single system. The Alpha Centauri system has fascinated people for generations. And the truth is simple. We have no current technology that could send humans there within a human lifetime. Beyond Alpha Centauri, the next nearest star is Barnard's star, about 6 light-years away. Sirius is about 8.6 light-years away. Betelgeuse is about 700 light-years away. Betelgeuse is also a red supergiant, so large that if you placed it where the Sun is, it would extend past the orbit of Mars. And all of these stars are still part of what we'd call our local stellar neighborhood. They feel like nearby names in astronomy, but the distances between us and them are so vast that we will probably never visit them. And here's a detail that turns distance into something emotional. The light you see when you look at Betelgeuse left that star around the time the Crusades were ending on Earth. You are literally seeing the past. Not as a metaphor, as a physical consequence of the speed of light, and at these distances, Earth is gone from view. The solar system itself becomes a point of light, and Earth is far too small and faint to be visible inside that point. So let's zoom out further. Because every star you can see with the naked eye, every single one belongs to our galaxy, the Milky Way. The Milky Way is a spiral galaxy containing somewhere between 100 billion and 400 billion stars. Our Sun is just one of them. The Milky Way is about 100,000 light-years across. Remember, Proxima Centauri is about 4.24 light-years away. The width of our galaxy is about 24,000 times that distance. If the distance to Proxima Centauri were 1 inch, the Milky Way would be about 2,000 feet across. That's taller than most skyscrapers. Our Sun sits about 26,000 light-years from the galactic center. We're in a minor spiral arm called the Orion Spur, about halfway out from the center. We're not in the middle of anything special. We're in the suburbs of the galaxy, in a relatively quiet region where stars aren't too densely packed. And this changes the meaning of small. At this scale, Earth's presence in the cosmos becomes conceptually different. Even our entire solar system is just a tiny point. The Sun, which seems so massive compared to Earth, is now just one ordinary star among hundreds of billions. And Earth is far too small to even register. Imagine compressing our galaxy into a structure 100 feet across. In that model, our entire solar system would be thinner than the width of a human hair. And Earth would be far, far smaller than that. At this scale, Earth wouldn't just be invisible. It would be smaller than an atom in the model. The Milky Way is a barred spiral galaxy. That means it has a central bar-shaped structure made of stars, with spiral arms extending from the ends of the bar. Our Sun is located in the Orion Spur, which is actually a minor arm connecting 2 major spiral arms, the Sagittarius arm and the Perseus arm. The galaxy rotates, but not like a solid wheel. Different parts rotate at different speeds. Near the center, stars orbit faster. Farther out, they orbit more slowly. Our Sun takes about 225 million years to complete one orbit around the galactic center. That is sometimes called a galactic year, or a cosmic year. Think about that. In the time it takes for our Sun to go around the galaxy once, entire species rise and fall on Earth. The last time the Sun was at this point in its orbit, dinosaurs were just beginning to emerge. The time before that, the supercontinent Pangaea was still intact. Earth has been around for about 20 galactic years. The universe has existed for about 60 galactic years. These timescales are almost impossible to hold in your head. But they matter, because scale is not just distance. Scale is time. The Milky Way has several distinct regions. At the center is the galactic bulge, a dense concentration of older stars. This region is about 10,000 light-years across. The stars there are packed much more densely than in our neighborhood. If you lived on a planet near the galactic center, your night sky would be filled with thousands of bright stars, making night almost as bright as twilight on Earth. And at the very center of the bulge sits Sagittarius A star, the supermassive black hole. This black hole has a mass of about 4 million times the mass of our Sun. It's relatively quiet now, but it occasionally flares up when gas, or even a star, falls into it. Around the galactic center are the spiral arms. These are regions where gas and dust are compressed, triggering star formation. The spiral arms appear bright because they contain many young, hot blue stars. These massive stars live fast and die young, rarely lasting more than a few million years. And because they die so quickly, they don't travel far from where they were born. So they remain concentrated in the spiral arms. Our Sun, being an older and more stable star, has had time to drift away from the spiral arm where it formed. We're now between spiral arms, in a quieter region. And that is probably a good thing for life on Earth. Spiral arms can be violent places. More supernovae, more intense radiation. Being between the arms gives Earth a safer environment. Surrounding the spiral structure is the galactic halo, a roughly spherical region containing old stars and globular clusters. The halo extends about 130,000 light-years from the galactic center. The stars in the halo are among the oldest in the galaxy, formed when the Milky Way was just beginning to take shape. The halo also contains dark matter. We can't see dark matter directly, but we can detect its gravitational effects. The Milky Way's dark matter halo extends even farther than the visible halo, possibly out to 600,000 light-years or more. Most of the Milky Way's mass is actually dark matter, not stars and gas. And the Milky Way is not isolated. It has numerous satellite galaxies orbiting it. The two most famous are the Large and Small Magellanic Clouds. Both are being slowly torn apart by the Milky Way's gravity and will eventually be absorbed. There are dozens of other, smaller satellite galaxies too. Most are dwarf galaxies containing only a few million stars. These satellites matter because they help us understand how galaxies grow. Large galaxies like the Milky Way form through mergers. The satellites we see today are the leftovers that haven't merged yet, and the Milky Way is moving through space toward another giant, the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will merge into a single large elliptical galaxy containing roughly 1.5 trillion stars in total. Don't worry about the collision. When galaxies merge, the stars are so far apart that actual collisions between stars are incredibly rare. The galaxies will pass through each other. Their gravity will pull them back. And over time, they'll settle into a single, larger structure. By then, the Sun will probably be dead anyway. So if humans still exist, we will have long since left Earth, or we won't be around to witness it. And this is the strange truth of cosmic scale. When you zoom out far enough, even events that sound dramatic, like two galaxies colliding, become slow, graceful rearrangements across billions of years. Now, hold on to the core question. We're not just touring facts. We're building a feeling. Because the farther out we go, the clearer the message becomes. Earth is not just small compared to planets. Earth is not just small compared to stars. Earth is small compared to the structures that hold stars. And once you understand the scale of our galaxy, the next step is inevitable. We have to ask what the Milky Way is part of. Because even a galaxy is not the end of the ladder. The Milky Way isn't the end of the ladder. It's just the next rung. Because once you understand that our entire solar system is a speck inside one galaxy, the next question becomes unavoidable. What is our galaxy part of? And this is where the scale starts to feel almost unreal, because galaxies don't float alone in space like isolated islands. They gather, they group, they cluster. And then those clusters gather into structures so large that, at a certain point, you stop thinking in terms of objects and you start thinking in terms of flows, like cosmic currents pulling entire galaxies through space. So let's zoom out again, not from a planet to a star, not from a star to a galaxy, but from a galaxy to the structures that hold galaxies together. Our Milky Way has neighbors, dozens of them, and together they form what astronomers call the local group. The local group contains about 50 galaxies, including the Milky Way. This is our immediate cosmic neighborhood. The largest member of the local group is Andromeda, also called M31. Andromeda contains about 1 trillion stars, which is more than twice what the Milky Way has. It's about 220,000 light-years across, more than twice the Milky Way's diameter. And Andromeda is on a collision course with us. In about 4.5 billion years, Andromeda and the Milky Way will merge into a single large galaxy. Now, that sounds catastrophic. But here's the important reality. When galaxies merge, the stars are so far apart that actual collisions between stars are incredibly rare. What happens instead is slower and stranger. The galaxies pass through each other. Gravity pulls them back. They swing around again, and over time, they settle into a single, large elliptical galaxy. By then, the Sun will probably be dead anyway. So if humans still exist, we will have long since left Earth, or we won't be around to see it. The next largest member of the local group is Triangulum, also called M33. It contains about 40 billion stars and is about 60,000 light-years across. It's smaller than the Milky Way, but still a respectable galaxy in its own right. The rest of the local group is made mostly of dwarf galaxies, small collections of a few billion stars or less. The Large Magellanic Cloud, which orbits the Milky Way, contains about 10 billion stars. The Small Magellanic Cloud has a few billion. Both are visible from the southern hemisphere as fuzzy patches in the night sky. And the local group itself spans about 10 million light-years. 10 million light-years. That sounds enormous, and it is. But in the language of large-scale cosmic structure, it's barely the beginning, because the local group is not floating alone either. It's part of something bigger, a much larger structure made of many galaxy groups and clusters. The local group is part of the Virgo supercluster. The Virgo supercluster spans about 110 million light-years, and it contains at least 100 galaxy clusters and groups. Altogether, those structures hold somewhere around 100 trillion stars. And within this supercluster, one region dominates: the Virgo cluster itself. The Virgo cluster is located about 54 million light-years from us, and it contains between 1,200 and 2,000 galaxies, thousands of galaxies in one gravitationally bound environment, some of them far larger than the Milky Way. And at the heart of the Virgo cluster is a galaxy called M87. M87 is a giant elliptical galaxy. It contains about 1 trillion stars. It's roughly 120,000 light-years across, similar in diameter to the Milky Way, but much more massive. And M87 is famous for something else. In 2019, the Event Horizon Telescope collaboration released an image showing the shadow of M87's supermassive black hole. That black hole has a mass about 6.5 billion times the mass of the Sun. Consider the sheer escalation here. The Milky Way felt enormous. Then you learned it's one galaxy among many. Then you learned it belongs to a group. Then that group is part of a supercluster. Then inside that supercluster is a cluster containing thousands of galaxies. And inside one of those galaxies is a black hole with billions of solar masses. And through all of this, Earth is not shrinking. Earth is simply becoming irrelevant to the scale. If we made a scale model where the Milky Way was the size of a coin, the Virgo supercluster would be about the size of a large city. Everything you've heard up to this point, the Sun, the solar system, the distances between stars, the Milky Way itself would fit on that coin in this model. And Earth would be far smaller than any particle you could see with a microscope. Now here's where the story gets even bigger. Because in 2014, astronomers discovered something even larger than the Virgo supercluster. They found that the Virgo supercluster is just a small part of an even more massive structure called Laniakea. The name comes from Hawaiian and means immeasurable heaven. And it fits. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies spread across 520 million light-years. That is not a typo. 520 million light-years. And here's what makes it feel less like a thing and more like a system. All these galaxies, including our Milky Way, are slowly moving toward the center of Laniakea. They're being pulled by the combined gravity of all that mass. The center of Laniakea, the point toward which everything is flowing, is called the Great Attractor. This is a region of space with such enormous gravitational pull that it's drawing in thousands of galaxies. And there's another twist. From our perspective, the Great Attractor sits behind the plane of the Milky Way. That means dust and gas in our own galaxy block our view of it. For decades, astronomers knew something massive was there, because they could measure its gravitational effects. But they couldn't see it directly. Using different types of light, radio waves, infrared, and X-rays, astronomers pieced together what the Great Attractor is. It isn't a single object. It's a region containing several massive galaxy clusters. And one of the largest structures in that region is the Norma cluster. But even the Great Attractor isn't the whole story. Recent observations suggest there is something even more massive beyond Laniakea, pulling it. A structure called the Shapley supercluster, located about 650 million light-years away. It contains thousands of galaxies, and it has a total mass of about 10,000 trillion times the mass of the Sun. At this scale, the Milky Way has become just one of 100,000 galaxies in Laniakea. And Earth is beyond invisible. Earth is beyond insignificant. It's approaching conceptual non-existence. Now step back and look at the pattern. When you map out the distribution of galaxies across the universe, you notice something. Galaxies aren't randomly scattered. They form clusters. Those clusters align along filaments and walls. And the result is a structure that looks less like a uniform fog of galaxies and more like a vast network, a cosmic web. Between the filaments of the cosmic web are enormous empty regions called voids. This structure exists because of how the universe evolved. In the very early universe, tiny density fluctuations existed in the distribution of matter. Some regions were slightly denser than average, others slightly less dense. Over billions of years, gravity amplified those differences. Dense regions attracted more matter, becoming denser. Less dense regions lost matter to their surroundings, becoming voids. And over time, the result is what we see today. Filaments of galaxies stretching across hundreds of millions of light-years, surrounding voids that are nearly empty. Laniakea is one filament in this web. There are many others. One of the largest known structures is the Sloan Great Wall, discovered in 2003. It's a wall of galaxies stretching about 1.37 billion light-years. It contains tens of thousands of galaxies arranged in a relatively thin sheet. If the Milky Way were the size of a coin, the Sloan Great Wall would stretch for miles. And there is another structure, possibly even larger, the Hercules Corona Borealis Great Wall. It might be the largest structure ever discovered. It stretches about 10 billion light-years across. That is about 73% of the radius of the observable universe. Structures this large created problems for cosmologists because, according to our models, there shouldn't have been enough time for something this large to form. And between these structures are the voids. The largest known void is the KBC void, about 2 billion light-years across. Inside this void, there are very few galaxies. It's not completely empty, but the density of galaxies is much lower than in surrounding regions. If you were somehow in the center of this void and looked out, the nearest significant galaxy clusters would be about 1 billion light-years away. From that vantage point, the universe would feel emptier than most humans can even imagine. These voids make up about 80% of the universe's volume. Most of space is empty. The galaxies, superclusters, and filaments occupy only a small fraction of the total volume. The universe is like a vast ocean with occasional islands of matter scattered throughout, and Earth sits on one of those islands. In a galaxy, that's part of a group. That's part of a supercluster. That's part of a supercluster of superclusters. That's part of a filament. In a cosmic web, at the scale of the cosmic web, Earth doesn't just become invisible. It becomes inconceivable. The difference in size between Earth and the cosmic web is so vast that human minds struggle to grasp it. Now let's zoom out one more time, to the largest meaningful boundary we can talk about. Not because it's the true edge of everything, but because it's the edge of what we can, even in principle, observe. The observable universe is the part of the universe we can theoretically see. It's limited by the speed of light and the age of the universe. Light from anything farther away than a certain distance hasn't had time to reach us yet. The universe is about 13.8 billion years old. You might think that means we can see 13.8 billion light years in every direction, but the universe has been expanding the whole time. Space itself has been stretching. So a galaxy that emitted light 13 billion years ago has moved much farther away during the time its light traveled toward us. The result is that the observable universe is about 93 billion light-years in diameter. That's the maximum distance from which light has had time to reach us, accounting for the expansion of space. Within this observable universe, astronomers estimate there are about 2 trillion galaxies. 2 trillion, each containing anywhere from millions to trillions of stars. And the total number of stars in the observable universe is estimated at around 200 billion trillion. To put that into an image, your mind can attempt to hold. If every star were represented by a grain of sand, you would need several Olympic-sized swimming pools to hold them all. And Earth? Earth would be so unimaginably small that no comparison captures it. You could fit so many Earths into the observable universe that the number becomes meaningless. With the observable universe scaled to Earth's dimensions, the Milky Way shrinks beneath subatomic particles, and Earth transcends measurability entirely, smaller than the fundamental particles that make up atoms. Now here's the final twist. The observable universe is only what we can see. The actual universe is almost certainly much larger. How much larger? We don't know. It might be a few times larger than what we can see. It might be thousands of times larger. It might be infinite. And if the universe is infinite, then the observable universe, no matter how huge it feels, is basically nothing. No matter how large 93 billion light-years seems, it's still 0% of infinity. And Earth would be even less significant in an infinite universe than it already is in the observable universe. Some theories in physics suggest the universe might be part of a multiverse, an infinite collection of universes. According to eternal inflation theory, the Big Bang wasn't a single event, but something that happens constantly, creating bubble universes that spawn more bubble universes. Our universe would be just one bubble in an infinite foam. Other interpretations of quantum mechanics suggest that every time a quantum event has multiple possible outcomes, the universe splits into multiple branches, with each outcome occurring in a different branch. This would create an infinite number of parallel universes. These ideas are speculative. We have no way to observe other universes. So, testing these theories is extremely difficult. But they arise naturally from well-established physics, which is why many physicists take them seriously. If the multiverse exists, then our entire universe, with its 93 billion light-year diameter and 2 trillion galaxies is just one universe among infinitely many. And Earth becomes even more vanishingly insignificant. Now, take a breath, because that's the furthest outward we can reasonably go. And it leaves you with a strange feeling, a feeling that your mind is standing at the edge of what it can represent. The universe is vast beyond comprehension. Earth is tiny beyond language. And yet, Earth is where everything we've ever known has happened. So in the next part, we're going to pivot. We're going to take this massive outward zoom and start bringing the meaning back. We'll look at what this scale does to our perspective, and we'll move into the sections on Earth's significance, rarity, and the way this cosmic context should change how we think about life here. Now, let's do something that might feel like a step backward. Because after talking about the observable universe, infinity, and even the possibility of a multiverse, it's easy to lose the emotional thread. So we're going to zoom back in for a moment. Not because the solar system is big compared to the cosmos, but because this is where the scale becomes personal again. This is where you can feel it. Even in our immediate neighborhood, Earth's smallness becomes obvious. Mercury, the closest planet to the Sun, is about 3,032 miles in diameter. That's only about 38% of Earth's diameter. Mercury's volume could fit inside Earth about 18 times. Mercury is a tiny, scorched world. Its surface temperatures swing from around 800 degrees Fahrenheit during the day to about -290 degrees at night. With almost no atmosphere, there's nothing to trap heat and nothing to protect the surface from constant impacts. Then there's Venus. Venus is closer to Earth in size. It has a diameter of about 7,521 miles, around 95% of Earth's diameter. People call it Earth's sister planet because of that similarity. But the surface conditions are completely different. Venus has a thick atmosphere loaded with carbon dioxide and clouds of sulfuric acid. The pressure on Venus is about 90 times higher than Earth's. That's like being about 3,000 feet underwater in Earth's oceans. And the heat is relentless. The average temperature is around 900 degrees Fahrenheit, hot enough to melt lead. Venus is actually hotter than Mercury, even though it's farther from the Sunday. And that's the lesson. Distance from the Sun is not the only thing that determines a planet's temperature. Atmospheres matter. A runaway greenhouse effect can turn a world into an oven. Venus also rotates in the opposite direction compared to most planets. While Earth and most planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. No one knows exactly why. It may have been knocked over by a massive impact billions of years ago. And Venus rotates very slowly. One day on Venus lasts 243 Earth days. With its orbit and rotation combined, the Sun rises in the west on Venus and sets in the east. Then comes Mars. Mars is smaller than Earth, but in many ways it feels more familiar than Venus. Mars has polar ice caps made of water ice and frozen carbon dioxide. It has seasons, although they're about twice as long as ours, because Mars takes about 687 Earth days to orbit the Sunday. We can see ancient riverbeds and lake beds on Mars. Mars once had liquid water on its surface. But something happened. Mars lost most of its atmosphere. And without a thick atmosphere, liquid water can't last on the surface. It freezes or evaporates. Today, Mars averages a frigid -80 degrees Fahrenheit. Equatorial summers can occasionally rise above freezing, but polar winters plunge far deeper. And the atmospheric pressure is less than 1% of Earth's. Why did Mars lose its atmosphere? Part of it is size. Mars is smaller than Earth, so its gravity is weaker. But the main reason is Mars lost its magnetic field. Earth's magnetic field is generated by motion in our molten iron core. That field acts like a shield, deflecting the solar wind, a stream of charged particles from the Sunday. Mars once had a magnetic field too, but its core cooled and solidified, shutting the field down. And without that protection, the solar wind slowly stripped away Mars's atmosphere over hundreds of millions of years. Mars has two small moons, Phobos and Deimos. Phobos is only about 14 miles across. It orbits so close to Mars that it goes around the planet 3 times in each Martian day, and Phobos is slowly spiraling inward. In about 50 million years, it will either crash into Mars or break apart from tidal forces, forming a ring around the planet. Between Mars and Jupiter lies the asteroid belt. Movies make it look like a dense minefield, but the reality is different. The asteroid belt contains millions of rocky objects, yet it's mostly empty space. You'd have to aim carefully to hit an asteroid, and the total mass of all the asteroids combined is less than 4% of the Moon's mass. The largest object there is Ceres. Ceres is round, shaped by its own gravity, which is why it's classified as a dwarf planet. Ceres has a diameter of about 588 miles, about as wide as Texas. NASA's Dawn spacecraft visited Ceres from 2015 to 2018 and found evidence of a subsurface ocean. Ceres might have more fresh water than all of Earth's lakes and rivers combined. Then you arrive at Jupiter. This is where the word big starts to mean something different. Jupiter has a diameter of about 86,881 miles. That's about 11 Earths across. But the real shock is volume. Jupiter's volume is so immense that 1,321 Earths would barely fill it. Jupiter contains more mass than all the other planets combined, and its gravity reaches out across the solar system, affecting comets and asteroids. Jupiter acts like a kind of cosmic vacuum cleaner, capturing objects that might otherwise threaten the inner planets. Some scientists think Jupiter's presence helped Earth by reducing the number of large impacts, making it easier for complex life to evolve here. Jupiter's most famous feature is the Great Red Spot. It's a storm larger than Earth, raging for at least 400 years. Wind speeds around its edges reach about 400 miles per hour. But the storm is shrinking. 100 years ago, it was about 3 times wider than Earth. Now, it's only about 1.3 times wider. If that continues, the Great Red Spot could disappear within our lifetimes. Jupiter has at least 95 moons, and more are found as telescopes improve. The 4 largest are the Galilean moons, discovered by Galileo in 1610. Io is the most volcanically active body in the solar system, constantly resurfaced by eruptions. Europa has a smooth, icy surface, crisscrossed with cracks, and beneath the ice there is likely a global ocean that could contain twice as much water as Earth's oceans. Ganymede is the largest moon in the solar system, even bigger than Mercury, and Callisto is heavily cratered, with one of the oldest surfaces in the solar system. Saturn comes next, almost as impressive. Saturn has a diameter of about 72,367 miles. It could swallow 764 Earth-sized worlds. But Saturn's signature is its rings. They are made of countless particles of ice and rock, ranging from tiny grains to house-sized boulders. The rings extend from about 4,300 miles to about 75,000 miles above Saturn's cloud tops. And yet, they are remarkably thin. In most places, only about 30 feet thick. No one knows exactly how old Saturn's rings are. They might have formed when Saturn did, around 4.6 billion years ago. Or they might be much younger, perhaps only a few 100 million years old, formed when a moon was torn apart by Saturn's gravity. Saturn has at least 146 known moons. Titan, the largest, is bigger than Mercury. Titan is the only moon in the solar system with a thick atmosphere, and its atmosphere is thicker than Earth's. The surface pressure is about 1.5 times Earth's sea level pressure. Titan's atmosphere is mostly nitrogen, like Earth's, but it also contains methane. Titan has stable bodies of surface liquid, but not water. It is too cold for that. Instead, Titan has lakes and seas of liquid methane and ethane. These hydrocarbons rain from the sky, carve river channels, and collect in low areas. Titan is the only place in the solar system besides Earth where we've confirmed stable bodies of surface liquid. Another moon that changes how you think about habitable is Enceladus. Enceladus is only about 313 miles across. It has geysers at its south pole that shoot water ice hundreds of miles into space. That water comes from a subsurface ocean. The Cassini spacecraft flew through these geysers and detected organic molecules, the building blocks of life. Enceladus is now considered one of the best places in the solar system to search for life. Uranus is strange in a different way. Its axis of rotation is tilted about 98 degrees from vertical. It's basically rolling around the sun on its side. That means one pole can experience continuous sunlight for about 42 years, followed by about 42 years of darkness. No one knows for sure why Uranus is tilted so dramatically. The leading idea is that it was hit by a large object early in the solar system's history. Neptune, the farthest planet from the Sun, is so distant it takes about 165 Earth years to complete a single orbit. Neptune was discovered in 1846, which means it has completed less than 2 full orbits since we first spotted it. And Neptune is violent. Wind speeds can reach up to 1,200 miles per hour, the fastest measured on any planet in the solar system. Voyager 2 observed a storm called the Great Dark Spot in 1989. But when the Hubble Space Telescope looked again in 1994, that storm had disappeared and new ones had formed. Neptune's weather changes quickly and unpredictably. Neptune has at least 16 known moons. The largest, Triton, orbits backward compared to Neptune's rotation. That retrograde orbit suggests Triton didn't form with Neptune, but was captured from the Kuiper Belt. And Triton is slowly spiraling inward. In about 3.5 billion years, it will crash into Neptune or break apart from tidal forces, forming a ring system. Beyond Neptune lies the Kuiper Belt, filled with icy bodies left over from the solar system's formation. Pluto is the most famous Kuiper Belt object. Pluto was considered the 9th planet from 1930 until 2006, when astronomers redefined what constitutes a planet. Pluto didn't make the cut because it hasn't cleared its orbit of debris. Pluto is about 1,473 miles across. It has 5 known moons, with the largest being Charon, which is about half Pluto's size. Pluto and Charon are so close in size that they're sometimes described as a binary system, orbiting a point in space between them. NASA's New Horizons spacecraft flew past Pluto in July of 2015, giving us our first close-up views. Those images revealed a complex world. Mountains made of water ice, vast plains of frozen nitrogen, a thin atmosphere extending much farther than expected, and a large heart-shaped region called Tombaugh Regio, named after Clyde Tombaugh, who discovered Pluto in 1930. There are other large Kuiper Belt objects too, classified as dwarf planets. These objects showed us the outer solar system is more populated than we once thought. Beyond the Kuiper Belt is the Oort cloud. No object in the Oort cloud has ever been directly observed. We infer it because of comets, especially long-period comets that take hundreds or thousands of years to orbit the Sunday. When a passing star's gravity disturbs an Oort cloud object, it can fall inward and become a comet. The Oort cloud extends from about 2,000 astronomical units out to about 100,000 astronomical units. That's nearly 2 light years. It's so far away the Sun's gravity barely holds onto it. And that brings us back to the point. Even in our own solar system, Earth is not large. Jupiter dwarfs it. Saturn could swallow it hundreds of times. And the Sun dominates everything, holding 99.86% of the solar system's mass. So Earth is small here. But Earth is not rare in one sense. It's not unique in being a planet. And we now know that because we've found worlds beyond our solar system. Since the first exoplanet was confirmed in 1992, astronomers have discovered over 5,500 planets orbiting other stars. Those discoveries revealed a universe full of variety. Some exoplanets are enormous. Hot Jupiters are gas giants that orbit very close to their stars. Some can be several times more massive than Jupiter. HD 189733b, for example, has a mass about 13 times Jupiter's, and it orbits so close to its star that a year there lasts about 3 Earth days. Other exoplanets are tiny. Kepler 37b is about the size of Earth's moon, with a diameter of about 2,400 miles. It orbits its star every 13 days. Some exoplanets orbit in the habitable zone, where liquid water could exist on the surface. Kepler 452b is one example. It is about 60% larger than Earth and lies about 1,800 light-years away. We will never visit it, but its existence matters because it tells you this. Earth is not alone in being a rocky planet roughly our size. There are probably millions or billions of Earth-sized rocky planets in the Milky Way. So what might actually be unique? As far as we know, it's not Earth's size. It's that Earth has life. Right now, Earth is the only confirmed example. We might find microbial life elsewhere in our solar system, maybe on Mars, or in the oceans of Europa or Enceladus. And there may be countless other life-bearing planets elsewhere. But today, we only know one. And that makes this small world precious. Now, to really understand Earth's scale, we have to look at stars, because stars vary wildly in size. The Sun is a fairly average star, a G-type main sequence star, sometimes called a yellow dwarf. Its diameter is about 864,000 miles. About 109 Earths could line up across the Sun's diameter, and about 1.3 million Earth-sized spheres could fit inside its volume. But many stars are smaller. Red dwarfs are the most common stars in the galaxy. Proxima Centauri has a diameter of about 129,000 miles. About 8.5 Earths could line up across Proxima Centauri's diameter. The smallest known star in the script is EBLM-J0, 555-57AB, with a diameter of about 68,000 miles. That is only about 8% of the Sun's diameter. It's barely large enough to sustain hydrogen fusion. Any smaller, and it would be a brown dwarf, a failed star that never got hot enough to ignite fusion. And on the other end of the scale are the giants. Betelgeuse, a red supergiant in Orion, has a diameter of about 617 million miles. That's about 700 times the Sun's diameter. If you placed Betelgeuse where the Sun is, it would extend past Mars's orbit. Earth would be deep inside the star, vaporized instantly. But Betelgeuse isn't the largest named here. UY Scuti is one of the largest known stars. It has a diameter of about 1.7 billion miles, about 1,900 times the Sun's diameter. If UY Scuti replaced the Sun, it would extend past Saturn's orbit. And its volume is so staggering that about 6.5 trillion Earth-sized spheres could fit inside. At that point, the numbers stop feeling like numbers. They become a kind of pressure on your imagination. And then there are the remnants. When stars die, they leave behind objects that can be small in size, yet extreme in mass. When a star like the Sun dies, it swells into a red giant, sheds its outer layers, and leaves behind a white dwarf. A typical white dwarf has a diameter of about 6,200 miles, only about 80% of Earth's diameter, but it can contain about half the mass of the Sun, compressed into an Earth-sized volume. Its density is about 1 million times the density of Earth. A teaspoon of white dwarf material would weigh about 5 tons on Earth. More massive stars can leave neutron stars. A neutron star might be only about 12 miles across, about the size of a city. Yet it can contain about 1.4 to 2 times the mass of the Sunday. Its density is so extreme that a teaspoon of neutron star material would weigh about 4 billion tons, and the most massive stars can collapse into black holes. where gravity is so strong that not even light escapes. Sagittarius A star, the black hole at the center of the Milky Way, has a mass about 4 million times the mass of the Sunday. Yet its event horizon is only about 17 times the Sun's diameter. M87's black hole, the one imaged in 2019, has a mass about 6.5 billion times the Sun's. Its event horizon is about 23.6 billion miles across. That's about 250 times the distance from Earth to the Sunday. And still, even that is small compared to the galaxy it lives in. All of this reinforces a strange truth. Size and importance are not the same thing. Earth is small, but Earth sits in a universe capable of making stars and black holes and structures that stretch for billions of light years. And somehow, on this small planet, matter learned to look back. Now, before we go even deeper into meaning, we need one more kind of scale shift. Not outward, and not inward to particles yet, but sideways, to history, because humanity did not always know any of this. For most of human history, we lived inside an illusion of centrality. And breaking that illusion is one of the most important stories we've ever lived through. Now let's bring everything together. We've looked at Earth from multiple angles. We compared it to the Moon, the Sun, the solar system, nearby stars, the Milky Way, galaxy clusters, superclusters, and the cosmic web. We looked at the structure of matter, and we looked at the scale of time. And every comparison points to the same conclusion. Earth is small. Not just small, tiny, almost impossibly tiny. When you compare it to the full scale of the universe, the observable universe spans about 93 billion light-years across. It contains about 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. And the total number of stars in the observable universe is estimated at around 200 billion trillion. Earth is one planet, orbiting one star in one galaxy among 2 trillion galaxies. If you selected a random star in the observable universe, the chances of picking the Sun are 1 in 200 billion trillion. And even if you somehow picked the Sun, you'd then have to select Earth out of 8 planets, dozens of moons, and countless asteroids and comets. The chances of randomly selecting Earth out of all objects in the observable universe are so small that the number is effectively 0. Earth is not just rare, it's vanishingly rare. But here's something else to consider. The observable universe is only what we can see. The actual universe is larger, possibly infinitely larger. And if it's infinite, then no matter how improbable something is, it will happen infinitely many times. There could be infinite copies of Earth out there, each with its own version of you listening to these words. That's speculative, of course. We have no way to observe beyond the observable universe. But it's a reminder that even our most extreme estimates of scale might still be underestimating the true size of everything that exists. And then, in 1990, something happened that made all of this feel real in a way numbers never can. The Voyager 1 spacecraft had completed its primary mission and was heading out of the solar system. And at that point, it turned its camera back toward Earth and took a photograph. In that image, Earth appeared as a tiny pale blue dot, less than a pixel in size, suspended in a beam of sunlight. That photo, taken from about 3.7 billion miles away, is one of the most profound images ever captured. Because it shows Earth as it really is in the context of space, a tiny speck floating in an enormous void. Astronomer Carl Sagan reflected on this image in his book Pale Blue Dot, and he wrote about what it really means. He pointed out that every human who ever lived their entire life on that tiny speck. Every king and peasant, every hero and villain, every creator and destroyer of civilization, all of them lived on that dot. All our triumphs and tragedies, all our wars and peace, everything that has ever mattered to humanity happened on something so small that, from a modest distance, it disappears entirely. And Sagan's point wasn't that this makes life meaningless. It was the opposite. This perspective should change how we see ourselves and how we treat each other. The petty disagreements that divide us, the borders we fight over, the resources we compete for, all of it plays out on a stage so small that, from even a little farther away, it would be invisible. And that doesn't make our lives less important. If anything, it makes them more precious. Because as far as we know, that pale blue dot is the only place in the universe where life exists. And conscious, intelligent life might be even rarer. And here's another detail that hits hard once you think about it. That pale blue dot photo was taken from a distance that's basically nothing on cosmic scales. 3.7 billion miles sounds enormous, but it's only about 40 times the distance from Earth to the Sun. It's barely out of the solar system. From the nearest star, Earth would be completely invisible, lost in the glare of the Sun. From another galaxy, our entire solar system would be invisible. And yet, that tiny pale blue dot is home to everything we know. Every thought, every emotion, every moment of joy and sorrow. All of it happened there. Now, there's a reason this feels so hard to really grasp. As humans, we evolved to understand things at human scales. We're good at judging distances of a few feet, a few miles. We can visualize objects from the size of a grain of sand up to mountains. But cosmic scales are beyond our intuitive grasp. When we talk about light years, billions of galaxies, and trillions of stars, the numbers start to lose meaning. Not because they aren't true, but because they're too large for our brains to convert into a real picture. We can do the math. We can write the numbers down. But we can't truly visualize what they mean. That's why analogies and scale models help. When we say the Sun is about 1 million times larger than Earth by volume, that's a fact, but it's hard to feel. When we say that if Earth were a marble, the Sun would be a sphere, about 10 feet across, that's easier to picture. But even those analogies break down at the largest scales. When we try to compare Earth to the observable universe, the numbers become so extreme that no analogy works. There's simply no way to make it intuitive. So the best we can do is accept the truth intellectually. Earth is tiny. We can't fully feel how tiny, but we can understand it. We can compare the numbers and recognize that Earth's size compared to the universe is so small that it's almost zero. And that realization can land in different ways. For some people, it feels humbling. For others, it feels frightening. But it can also be liberating. Because if Earth is that small, then from a cosmic perspective, our problems are also small. The conflicts we engage in, the status we chase, the things we worry about, they matter on Earth because Earth is where we live, but they mean nothing to the universe. And that doesn't mean we should stop caring. Our lives matter to us, and they should. But a cosmic perspective can keep things in proportion. It can remind us that we're all on the same small world, sharing the same tiny speck of dust in a vast cosmos. So where does all this leave us? We set out to discover how small Earth really is. And the answer is clear. Earth is incredibly, almost unimaginably small. Compared to the Sun, Earth is tiny. Compared to Jupiter, Earth is small. Within the Milky Way's 100,000 light-year expanse, Earth doesn't merely shrink, it ceases to register as anything measurable. Against Laniakea's 520 million light-year breadth, Earth transcends mere invisibility. It approaches conceptual non-existence. Measured against the cosmic web's filaments, Earth's dimensions fall below any meaningful threshold. If the observable universe were a vast ocean, Earth wouldn't be a grain of sand on a beach. It would be smaller than a single atom in that grain of sand. Actually, it would be far smaller than that. There's simply no adequate comparison. But Earth is also precious. As far as we know, it's the only place where life exists. The only place where consciousness has arisen. The only place where beings like us can look out at the cosmos and wonder about their place in it. Size isn't everything. What matters is what's here, and what's here is remarkable. Life in all its diversity. Consciousness capable of understanding the universe. Art, music, love, joy, the things that make existence meaningful. Earth might be small, but it's our home. And in a universe that's mostly empty space, mostly cold and dark and hostile to life, a small, warm planet teeming with life is incredibly special. The universe is vast. Earth is tiny, but Earth is home. And sometimes that's enough. Now, it's worth reflecting on how we came to understand all this. Because for most of human history, we had no idea how small Earth really is. And the story of how we learned it is one of the most important shifts in human perspective that ever happened. Historical cosmology and changing perspectives. It's worth reflecting on how we came to understand any of this at all. For most of human history, we had no idea how small Earth really is. Ancient people believed Earth was the center of everything. The sky felt like a dome overhead, with lights fixed to it, and the sun, the moon, and the planets seemed to move around us. And based on what you can observe with your own eyes, that view is understandable. When you stand on Earth and look up, it certainly appears that everything revolves around us. The sun rises in the east and sets in the west. The moon moves through its phases. The stars wheel overhead in predictable patterns night after night. So people built models that matched what they saw. Greek philosophers like Aristotle developed elaborate models of the cosmos with Earth at the center. These models worked reasonably well for predicting planetary positions. But the explanations grew more and more complicated over time, because planets didn't move in simple circles around Earth. They moved in circles that moved in circles, epicycles. And for nearly 2,000 years, this geocentric model dominated Western thought. It wasn't just astronomy, it was philosophy, it was religion, it was identity. If Earth was at the center, then humans were central to creation. We were special, we were the point of it all. The cosmos existed for us. Then came the first major challenge. In the 16th century, Nicolaus Copernicus proposed something radical. The sun, not Earth, was at the center. Earth was just another planet orbiting the Sunday. This heliocentric model was simpler and more elegant than the geocentric one. It didn't require epicycles stacked on top of epicycles. Planets moved in relatively simple paths around the Sunday. But Copernicus's model was controversial for a reason that had nothing to do with math. It challenged a deeply held belief about humanity's place in the cosmos. If Earth wasn't at the center, did that mean we weren't as important as we thought? In the early 17th century, Galileo Galilei provided evidence that pushed this argument from theory into reality. Using one of the first telescopes, Galileo observed the phases of Venus. That observation showed Venus must orbit the Sun, not Earth. He also discovered 4 moons orbiting Jupiter, proving that not everything orbited Earth. Those observations were a turning point. And they came with consequences. Galileo faced opposition from the Church. He was tried by the Inquisition in 1633 and forced to recant his support for heliocentrism. He spent the rest of his life under house arrest. But the evidence didn't go away. Other astronomers confirmed what he saw. Slowly, the heliocentric model gained acceptance. Then Johannes Kepler refined the model even further. Kepler showed that planets orbit in ellipses, not perfect circles. And later, Isaac Newton explained why planets move the way they do through his law of universal gravitation. By the 18th century, heliocentrism was firmly established. Earth was no longer the center of the cosmos. We orbited the sun like the other planets. But even then, people still held on to the idea that maybe the sun was special in a different way. Maybe the sun was at the center of the universe. After all, it was the biggest thing we knew. Surely it had to occupy some privileged position. Then came another shift. In the early 20th century, astronomer Harlow Shapley studied globular clusters, dense collections of stars that orbit the Milky Way. By mapping their positions, Shapley determined the size and structure of the galaxy, and he showed that the Sun was not at the center of the Milky Way. We were about 2/3 of the way out from the center, in a minor spiral arm. So we weren't at the center of the solar system. And we weren't at the center of the galaxy. Each discovery pushed us farther from the middle and forced us to confront something uncomfortable. We weren't special in the way we assumed we were. Then, in the 1920s, Edwin Hubble made an even more profound discovery. He observed galaxies beyond the Milky Way and measured their distances. That showed the Milky Way wasn't the entire universe. It was just one galaxy among many. Hubble also discovered that galaxies are moving away from us, and the farther away they are, the faster they're receding. That led to the Big Bang Theory, the idea that the universe began in a hot, dense state and has been expanding ever since. And with that, the universe exploded in size. It wasn't a sky dome. It wasn't a galaxy. It was billions of galaxies, each containing billions of stars. And Earth was one planet orbiting one star in one galaxy among billions. Not central, peripheral, ordinary, insignificant, in cosmic terms. And in the decades since, our understanding has continued to expand. We've discovered exoplanets, showing planets are common around other stars. We've mapped the cosmic web, revealing structure on scales of billions of light years. We've measured the expansion rate of the universe and discovered dark matter and dark energy. Each discovery reinforces the same message. The universe is vast. Earth is tiny. But strangely, that hasn't made life meaningless. If anything, it has made it more precious. Because in all that vastness, Earth is the only place we know where life exists. The Fermi paradox. And once you accept how enormous the universe is, a question naturally rises to the surface. If life is possible, shouldn't it be common? And if life is common, where is everyone? This question is known as the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" during a lunch conversation in 1950. The paradox is simple. The universe is old and vast. Even if intelligent civilizations are rare, there should still be many scattered across the galaxy. Some should be millions or billions of years older than us. They should have had time to colonize the galaxy. So why haven't we detected any sign of them? There are many proposed solutions. One is that intelligent life is incredibly rare. Maybe the jump from simple life to complex life is extremely difficult. Maybe intelligence rarely develops. Maybe technological civilizations tend to destroy themselves shortly after developing advanced technology. If any of these are true, we might be the only intelligent species in the galaxy, or even the universe. Another possibility is that civilizations exist but are staying quiet. Maybe they've learned that broadcasting your presence is dangerous. Maybe they're deliberately avoiding contact with other species. Maybe they're waiting for us to reach a certain level of development before revealing themselves. Or maybe civilizations exist, but communicate in ways we can't detect. We've been listening for radio signals, but maybe advanced civilizations use something else, quantum communication, or technologies we haven't imagined yet. There's also a simpler, more sobering possibility. Space is just too big. Even if civilizations are common, the distances between stars are so vast that contact is effectively impossible. A radio signal traveling at the speed of light would take years, decades, or centuries to reach even nearby stars. A reply would take just as long. A conversation would be impossibly slow, and physical travel is worse. With our current technology, traveling to another star would take thousands, or tens of thousands of years. Even with hypothetical future technology, journeys between stars could still take decades or centuries. So the galaxy might be filled with civilizations that will never meet. Not because they're not there, but because the distances are too great to cross. This isolation is one consequence of Earth's smallness. We're tiny, and we're separated from other potentially habitable worlds by vast gulfs of empty space. Even if life exists elsewhere, we might never know. The universe's sheer scale might ensure we remain alone in practice, even if we're not alone in reality. The origin of life and the rarity question. Earth's smallness raises another question that's just as profound. How did life arise here? Was it inevitable? Or was it a cosmic accident? Something unbelievably unlikely that just happened to occur on our tiny planet. We don't know the answer. We have only one example of life on Earth. Every living thing on our planet, from bacteria to blue whales, shares a common ancestor. All life on Earth is related. We all use the same genetic code, the same basic biochemistry, and that suggests life arose once on Earth, and everything living today descended from that original life form. But how did that original life form arise? We don't know. The origin of life is one of the biggest unsolved questions in science. We know that about 4 billion years ago, Earth had liquid water and a variety of chemical compounds. And somehow, in that environment, non-living chemicals organized into something that could reproduce and evolve. But the details remain mysterious. Some scientists think life arises easily wherever conditions are right. In that view, the universe might be teeming with life. Others think life requires an incredibly unlikely series of events. In that view, life might be extraordinarily rare, perhaps unique to Earth. And then there's the question of complex life. Simple life, single-celled organisms, might be common. But complex life, multicellular organisms with specialized tissues and organs, might be much rarer. On Earth, simple life existed for about 3 billion years before complex life appeared. That's a long time. Maybe the jump from simple to complex is very difficult. And intelligent life might be rarer still. Intelligence, at least the kind humans have, might require a very specific set of conditions. It might be so rare that we're the only intelligent species in the galaxy, or even the universe. And if that's true, then Earth's smallness takes on a completely different meaning. We might be tiny, but we might also be carrying something unbelievably precious. Consciousness, intelligence, the ability to understand the universe. These might be extraordinarily rare in the cosmos. Earth, small as it is, might be the only place in billions of light years where the universe has become aware of itself. That is a staggering responsibility. Responsibility and the future. It means what happens on Earth matters not to the universe, which doesn't care but to the universe's ability to know itself. If we destroy ourselves, if we render Earth uninhabitable, we might be extinguishing the only light of consciousness in a vast, dark cosmos. So let's look ahead. What does the future hold for Earth in the short term? In the next few million years, Earth will remain largely as it is. Continents will continue drifting slowly, the climate will change, but Earth will remain habitable. Life will continue evolving. And if humans survive, we will continue to develop and change. In the longer term, about 1 billion years from now, the sun will start to heat up as it ages. The oceans will begin to evaporate. Earth's surface will become increasingly inhospitable, and complex life will struggle to survive. Eventually, Earth will become too hot for any life as we know it. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin fusing helium. It will expand into a red giant, growing so large that it will likely engulf Mercury and Venus. Earth might survive on the outer edge of the sun's expanded atmosphere, but it will be a scorched, lifeless rock. Eventually, the sun will shed its outer layers and become a white dwarf. And Earth, if it survives, will orbit a small, dim star that provides no warmth. A frozen, dead world, in permanent darkness. But that's billions of years away. For now, Earth is a vibrant, living world, the only world we know that's teeming with life. And there's another future to consider. The future of human exploration. If humans survive and continue to develop technology, we might one day leave Earth. We might establish colonies on Mars, on the moons of Jupiter and Saturn, perhaps even in orbit around other stars. If that happens, Earth will always matter as our birthplace. But it won't be our only home. will be a spacefaring civilization spread across multiple worlds. Earth will be one planet among many that humans inhabit. And even then, the universe will remain humbling. The Milky Way is just one galaxy among trillions. Human civilization, no matter how far it spreads, will occupy only a tiny fraction of the cosmos. Conclusion: Earth's tiny yet valuable role in the cosmos. As we approach the end of this journey, it's worth pausing to consider what makes Earth truly special. Despite the universe's vast scale, it operates on the same principles of physics and chemistry everywhere. Stars form, burn, and die according to universal laws. Planets coalesce from dust and gas through gravity. These processes happen throughout the cosmos, in billions of galaxies around trillions of stars. Yet, Earth stands apart in one crucial way. It harbors something that might be extraordinarily rare, or even unique: the emergence of complexity from simplicity, the organization of matter into living systems, and most remarkably, the evolution of consciousness capable of comprehending its own cosmic insignificance. Think about that paradox. We're standing on a planet so small it essentially doesn't exist at cosmic scales. And yet, from this vanishing point, we've managed to measure and map the observable universe. How did unconscious matter organize itself into conscious observers? How did atoms, following blind physical laws, arrange themselves into beings capable of wonder, capable of asking questions about their own existence? The fact that you're listening to these words right now, understanding them, contemplating your place in the universe, might be more remarkable than any vast structure we've discussed. Earth might be tiny, but it has accomplished something that billions upon billions of other worlds apparently have not. It has produced a biosphere, an interconnected web of life spanning millions of species. It has produced intelligence capable of technology, of art, of science. It has produced beings who can look up at the night sky and through thought and observation determine that those points of light are distant suns, that our galaxy is one among trillions, that the universe is expanding and had a beginning. And that brings us to responsibility. If life is rare and consciousness is even rarer, then what happens on Earth takes on cosmic significance. We are quite possibly the universe's only way of knowing itself. Through us, through our observations and our science, matter has become aware of matter. That's either common, repeated countless times across the cosmos, or it's extraordinarily special. We don't know which. But until we find evidence of life elsewhere, we have to act as though Earth's biosphere, and especially its intelligent life, is precious beyond measure. Every species that goes extinct on Earth isn't just a loss for our planet. It might be a loss for the entire universe. Every potential future where humans fail to survive and spread isn't just a tragedy for our species. It might mean the permanent silencing of the universe's ability to comprehend itself in this corner of space. That perspective should change how we treat our planet and how we treat each other. The conflicts between nations, the competition for resources, the damage we do to Earth's ecosystems, this all takes on a different character when we remember where we are. We're not fighting over a large territory. We're fighting over different parts of a dust speck. We're not competing for the resources of a vast world. We're competing for the resources of something almost too small to measure against cosmic scales. And if other intelligences exist out there, looking back at us from distant worlds, what would they think of how we've chosen to use our brief moment of awareness? Would they understand our divisions and conflicts? Or would they see them as incomprehensible, given the preciousness of consciousness in a vast, mostly dead universe? Looking far ahead, beyond Earth's eventual demise, we can ask, what is humanity's ultimate potential? If we survive the next few centuries, if we learn to live sustainably on our small planet, or spread to others, what might we become over millions or billions of years? The universe will remain largely hospitable to life for trillions of years. Stars will keep burning. Planets will keep orbiting. The laws of physics that allow complexity to exist will remain in force. If humanity, or its descendants, survive and spread, we could potentially outlive not just our planet, but our Sunday. We could witness the gradual evolution of our galaxy. We could see stars being born and dying. We could watch as the Milky Way and Andromeda merge into a new galactic structure. Our descendants might spread not just through our galaxy, but to others. They might develop technologies we cannot imagine, technologies that make interstellar travel practical or even routine. They might transform themselves, merging with machines, or adopting new forms better suited to space travel or life in extreme environments. They might seed the galaxy with new life, taking Earth's biosphere and replicating it on thousands or millions of other worlds. The fact that you're listening to these words right now, understanding them, contemplating your place in the universe, might be more remarkable than any vast structure we've discussed. Earth might be tiny, but it has accomplished something that billions upon billions of other worlds apparently have not. It has produced a biosphere, an interconnected web of life spanning millions of species. It has produced intelligence capable of technology, of art, of science. It has produced beings who can look up at the night sky and through thought and observation determine that those points of light are distant suns, that our galaxy is one among trillions, that the universe is expanding and had a beginning. And that brings us to responsibility. If life is rare, and consciousness is even rarer, then what happens on Earth takes on cosmic significance. We are quite possibly the universe's only way of knowing itself. Through us, through our observations and our science, matter has become aware of matter. That's either common, repeated countless times across the cosmos, or it's extraordinarily special. We don't know which. But until we find evidence of life elsewhere, we have to act as though Earth's biosphere, and especially its intelligent life, is precious beyond measure. Every species that goes extinct on Earth isn't just a loss for our planet. It might be a loss for the entire universe. Every potential future where humans fail to survive and spread isn't just a tragedy for our species. It might mean the permanent silencing of the universe's ability to comprehend itself in this corner of space. That perspective should change how we treat our planet and how we treat each other. The conflicts between nations, the competition for resources, the damage we do to Earth's ecosystems, this all takes on a different character when we remember where we are. We're not fighting over a large territory. We're fighting over different parts of a dust speck. We're not competing for the resources of a vast world. We're competing for the resources of something almost too small to measure against cosmic scales. And if other intelligences exist out there, looking back at us from distant worlds, what would they think of how we've chosen to use our brief moment of awareness? Would they understand our divisions and conflicts? Or would they see them as incomprehensible, given the preciousness of consciousness in a vast, mostly dead universe? Looking far ahead, beyond Earth's eventual demise, we can ask, what is humanity's ultimate potential? If we survive the next few centuries, if we learn to live sustainably on our small planet, or spread to others, what might we become over millions or billions of years? The universe will remain largely hospitable to life for trillions of years. Stars will keep burning. Planets will keep orbiting. The laws of physics that allow complexity to exist will remain in force. If humanity, or its descendants, survive and spread, we could potentially outlive not just our planet, but our Sunday. We could witness the gradual evolution of our galaxy. We could see stars being born and dying. We could watch as the Milky Way and Andromeda merge into a new galactic structure. Our descendants might spread not just through our galaxy, but to others. They might develop technologies we cannot imagine, technologies that make interstellar travel practical or even routine. They might transform themselves, merging with machines, or adopting new forms better suited to space travel or life in extreme environments. They might seed the galaxy with new life, taking Earth's biosphere and replicating it on thousands or millions of other worlds. Or they might fail. Civilizations might be fragile things, brief sparks of consciousness that flicker and die on cosmic timescales. We might destroy ourselves through war, through environmental collapse, Through technologies we develop faster than we develop the wisdom to use them. Earth might return to a world of simpler life, or even to a lifeless state, and the universe would continue on, vast and uncaring. The choice, to the extent we have one, is ours. Earth is tiny, yes. Our individual lives are brief, yes. But the cumulative effect of billions of humans making choices, developing technology, creating knowledge, and passing it forward has brought us to a pivotal moment. We are the first species on Earth capable of comprehending the cosmos. We're also the first capable of either spreading life beyond our planet or extinguishing it entirely. We've covered a lot of ground tonight. We started with Earth and zoomed out, comparing it to larger and larger structures until we reached the observable universe itself. And along the way, we discovered something profound. Earth is small, smaller than most people realize. When you compare it to stars, galaxies, and cosmic structures, Earth becomes so tiny it almost disappears from view. In a scale model of the observable universe, Earth would be far smaller than an atom, smaller than anything you could possibly see or measure. For all practical purposes, non-existent. But Earth is also home. Every human who has ever lived has lived here. Every thought, every emotion, every achievement, everything happened on this small planet. Earth might be tiny in the cosmic sense, but it's everything to us. And here's the remarkable part. We can understand this. We can comprehend, at least intellectually, how small we are. We can look out at the universe and grasp its scale. That's extraordinary. Out of all the planets in all the galaxies, Earth produced beings capable of understanding the universe. We might not be alone in this. There might be countless other civilizations out there looking up at their own skies and wondering about the cosmos. But we don't know that for certain. Right now, Earth is the only place we know where conscious life exists. That makes Earth precious beyond measure. Size doesn't determine value. What matters is what's here. And what's here on this tiny planet is something remarkable. Life, consciousness, the ability to wonder, to question, to seek understanding. So yes, Earth is small, but it's also irreplaceable. It's the only home we've ever known. And in a universe that's vast and mostly empty, a small world full of life is something to treasure. The next time you look up at the night sky, remember what you've learned. The stars you see are part of the Milky Way, our home galaxy. Those stars are suns, many with their own planets, and our galaxy is just one of trillions scattered across an almost unimaginably vast cosmos. Earth is tiny in all that vastness. But Earth is home, and that matters more than size ever could. Thank you for joining me on this journey across the cosmos. If you found this exploration meaningful, consider liking this video and subscribing so you don't miss the next one. And remember, you're standing on a planet that's tiny beyond comprehension when compared to the universe. But you're also standing on the only world we know that's home to life, consciousness, and wonder. That's something to hold on to. Sleep well tonight, knowing that you're part of something vast and beautiful. The universe is enormous. Earth is tiny. But Earth is precious. And you living on this small world are part of its story. Good night. See you on the next video.